So in this video we will be going through image steganography, if I'm pronouncing it right. So this means basically how do we hide data in images. And the notebook that I will go through here is already uploaded on GitHub and along with the scripts as well, so we will see that later. The link is added in the description, so you can go through it along with me. Alright, so what exactly is what do we mean by hiding data in image? So whenever we have an image, it is made up of pixels, right, which are some binary values, not binary values, I mean pixel values, so which are internally stored as binary values. So we will take leverage of that thing and using bit plane slicing. So if you don't know what bit plane slicing is, I would recommend you to go through another video that we have done in the past, where we have discussed about bit plane slicing in detail. So in this one I will be assuming that you are aware about bit plane slicing, because we'll be using that extensively in this one. Okay, so how do we approach the problem of hiding data in images? So in final objective of this video is that given an image and a hidden message, we want to hide that message in the image such that if anyone sees it, the image are basically not distinguishable, but still one would have a hidden message and one is the normal image. And then once we have that image which contains the hidden message, how do we get the message, or how do we extract the hidden message? So these are the two phases basically. One is the encoding phase and the second is the decoding part. So the steps that I will follow here are something like this. So first is I'm going to convert the hidden message into binary. So the hidden message will be a string. In order to hide it in the image, so I will convert it to binary. The second thing is I will extract the lowest bit plane. Now this is regarding the bit plane slicing. So I will extract the lowest bit plane of all the pixels. And why lowest? Because the lowest bit plane stores the least important detail for a given pixel. So we can change the value in the lowest bit plane and still the overall image will be similar, or I mean almost the same. Then once we have the hidden message in binary and the lowest bit plane, I will merge my message into that. And once I merge the message, I will hide the message, I will merge this lowest bit plane back to the image, and then we will see how to decode the image. Okay, so let's get going. Now first of all, the libraries that we need for this are CV2 to work around with images, then NumPy to play around with matrices, and to show the image I will use matplotlib.pyplot, which is imported as PLT. So these are the basic libraries that we normally use. Now let's import any given image. So in this one I'm using this $image.tiff, and this looks something like this here. Alright, so it's a $image. Now let's see how it looks. We've already seen it, but let's plot it using PLT, and this is how it is. Now it's a three-dimensional image, so it has BGR. Now for our task we just need a single channel, so we will extract any one of it. In this one I'm using the blue channel, and we can extract any one, so it doesn't make any difference. Alright, so now we will choose later this blue channel image. So now the first thing, given a hidden message, I need to convert it into binary, right? So given any message, so any message can be basically any hidden message. So I will write this is a hidden message. So I cannot use this message and hide it straight away into the image. I need to convert it into binary form. And what I mean by binary, so first of all I will convert each of the characters into ASCII values. So how do we convert into ASCII values? So basically let us say T. So I will use dot encode ASCII. Alright. No, wait, am I doing something wrong? Yeah. So yeah, now 116. So the ASCII value for T is 116, and similarly for each of the characters I will do it. So if I just take the value here like this. So now this 116, 104, 105, these are the ASCII values of these alphabets here. Okay. So once I have the ASCII values, then I would convert it into binary representation, and this is done using this np.binary repr. I'm passing the width as 8 because like like we want to store it as a 8-bit value, so that each of the characters, they have a uniform length of 8. Now how would this look like? Let's say the number is 115. So np.binary repr 115, and width is 8. So it will return a string which will be something like this, and this is the binary representation of this value, and this further is the ASCII representation of one of those characters. So similarly we will do this for all of the characters here, and this function will do that. Now one thing more is we are going to add additional character to the hidden message, which is the end character, and this we will use while decoding. So it will help us to know, okay, now our hidden message has ended, now we can stop our decoding process, and we will see it later when we will use it again. Given these two input, we will first add the end character to the hidden image, then we will get the ASCII values. Now from the ASCII values we will get the hidden message binary using the same function we looked above. Then we will convert it, because it is a string, we will convert it into a NumPy array here. We will first convert it to a list, because there are many characters like this, and then we will convert it into a NumPy array with a particular data type, int64. So let's see how it goes. So let's say the hidden message that I want to hide is they are going to rob the bank, and this looks like a message to be encoded, because yeah, it seems to be a very pretty information. So let's see if we pass this hidden message into this function, how it looks like. So if I run this one, so what am I doing here is I'm storing this into a variable, and then I'm passing this variable in these functions that we defined above. So let's see. Okay, so when I run this, I get some values of zeros and ones, and again it might be a little like strange, but this actually means this information here. Wow. So yeah, that's it. Now also, like, since we discussed above that each character will represent 8 values here, so just to make sure that this value is correct, we are going to assert a condition here. So the length of the binary message should be 8 times the hidden message, or also we are adding an additional character here. So if the length of the hidden message is, let's say, n, then its binary representation will have n plus 1 times 8 total characters, and we can assert it here, right? So the length of input sentence is 30, it has 30 characters including the space, and our binary conversion will have 248, which is 31 times 8. Alright, so this is the first function that we have written here, so converting hidden message into binary, and we just did that. So now the next thing is, how do I extract the lowest bit plane? Now again, I'm assuming that you know what we mean by bit plane, and what is the least significant bit plane and the most significant bit plane, and this is actually pretty much easy. So what I have done here is, so this function bit plane slicing, it takes in input as image and bit plane. But what's really happening here is, so this can be seen as a pixel, a single pixel, and given this pixel we convert it into binary representation, and then once we have the binary representation we extract the particular value that we want. So this runs for a pixel. An image is basically a collection of pixels, so we need to run over all the pixels. So for this one I will need to vectorize this function, and that is done by using np.vectorize. Alright, so again we have already used this function earlier in our previous video, so I will not go much into it. And you can even consider it as a black box. We just pass an image and it will give us the particular bit plane. In this example we will be using the lowest bit plane. So just run it, and to extract the lowest bit plane, as I said earlier, we'll be using the blue channel, and I pass 1 and it will give me the lowest bit plane. Now remember, the lowest bit plane will also have the same size as the same height and width as the blue channel. Now let's see how does it look like. So it looks like something like this, basically gibberish values but it does contribute to the image, to the overall image, which was this. So basically we are just extracting all the lowest bit planes of all the pixels, and this is what we get. Okay, so the part 2 is done, which is extracting the lowest bit plane. Now next we have is mix the decoded message into the lowest bit plane. So we have the bit plane, we have the hidden message into binary representation. How do I mix both of them? So now we will see that. So for that we will use this function, add code to bit plane. It takes 2 input, bit plane and binary message, and we already have both of them. So this is the bit plane and this is the binary message. So what exactly is done here? So first of all, let's see what bit plane looks like. So if I print this one, you can see it is also a collection of 0. Basically there are many ones as well. I'm just I mean, it is also a binary representation. It also has zeros and ones, and so does our hidden message. So now we need to mix both of them. So how I did it was, first of all, let's flatten it. Currently it is a 2-dimensional array, so let's flatten it, and by flattening it we mean converting to a single dimension. Then we take the length of the hidden message. So this was the bit plane and this is the hidden message, and what we do is we change the first n. So if the length of the hidden message in binary is n, we replace the first n values of this bit plane flattened to our binary message, and once we do that we again reshape it to the original, like how it was initially here, and then we return it, right? So we just putting our hidden message into the lowest bit plane. So once I run this, I get this as n plane coded. Let's see the shape. The shape would be same. Let's see how it looks like. Just need to replace a few variables. Okay, so this looks like this, and well, can you find any difference between this image and this image? Well, you know that now this one contains our hidden message, but if you just look at it, I mean, it's surely, and I'm not sure, like we can see and tell that they are different. It's not. Now the next thing is, given our lowest bit plane with our hidden message, let's add it back to the image. So how do we do that? Again, we use the bit plane slicing to do that. We take the image. So this function takes the image and the bit plane. It breaks down the image into its bit planes and then adds them back. But while adding them back, the lowest bit plane, we don't use the original one. Basically we add this one. So let's see what we are doing here. So first of all, we break it into the bit planes. So this is the most significant bit plane, so this contributes the most to the final image. Then we have 7 bit, 6 bit, 5 bit, 4 bit, 3 bit, 2 bit, and then we add them back together. But instead of adding the 1 bit, we add our hidden, like the bit plane which contains our hidden message. Alright, so if I run this one, so I run this, it takes a little bit of time and then it runs. So this is our image back. Again, you can't tell the difference between this one and the one we started working with, but we know the difference, right? It contains the hidden message. Now since this is the blue channel, we will merge the green and red back together, and then we can save the image. So this is the encoding part done. We have successfully hidden our message inside the image. Now how do we get our message back? How do we decode our image to get the hidden message? So for that we will perform a series of tasks which is opposite to what we did in the encoding phase. So for example, this is the function that decodes the message. So it takes two arguments. First is the image, which is the image where the message is hidden, and again, like this is, we are assuming that it is the first channel of the image where the message is hidden, and also in the first channel it is the lowest bit plane, right? So these because we have encoded it this way, so we need to decode it in the same way as well. And then the end character, and as I said, like we will use this in the decoding phase, so we will use it here. So the first thing is we will extract the first channel similar to what we did above, and then we get the lowest bit plane. Again, it's quite similar to what we did above. And once we have the lowest bit plane, we pass it to this function here, get message from plane. Now let's see what's happening here. So we pass in the plane and we pass in the end character. So what this function does is, given a input as a bit plane, it extracts the message and it's return the message. And how it does it? First of all, it flattens the given plane. Again, we have done this above. Then it converts it into this shape, -1,8, so that we can easily loop through it. And to make sure that this doesn't give an error, we are using this line here. So to make sure that the final length is divisible by 8, otherwise this will give an error. Now why 8? Because each of our single character is encoded as 8 binary values, so that is why we are using 8 here. So then we just need to go through each set of 8 binary values, because we know this is how we had hidden it in the first case. So we will loop through it and then get the character, which is using this function. And it's similar, like we have the binary value, we convert it to get the ASCII value, and we convert it to get the character. So quite the opposite thing that we did earlier. And once we have that, we join it together and we return it. Alright, so let's see how does it work for our image here. So if I run decode function, I need to run this. Oh, okay, yeah, now it is running. So they are going to robe the wing. So this is what we had done earlier, like the message we had hidden earlier. Now okay, so let's see how it works for the image that we had stored, because in the above cells we had stored the image or saved the image as coded image.png. Now let's load it and see whether it works or not. So I will load the image using cv2.imread, and then let's run this. So this is the shape, and then I need to pass this to the function decoded image, and yeah, this runs. But it may fail if, so it's running in this case here, but if we save this image as JPEG, then it may not run, because JPEG is low-C compression. It changes some of the values, in which we don't want here. So this will only work if we use some lossless compression like PNG. Now once gone through all the notebook, once we get an idea of how we made this thing to work, we can actually move it out into scripts, because that makes it much more easier to run it. So this is our script here, main.py, and it is further calling helper functions.py, and basically I've just added all the functions from the notebook to here. So it has two scripts, encode.py, which is this one, and decode.py, which is this one. So let's see how we can run this from the terminal. So to encode any message to an image, we need to run python encode.py -i image path. So -i, and we need give the image path, then -m we give the message, and then -s we give the save location. And to decode it, we need to run python.decode.py and give image path as argument. And also if we give this show, it prints the hidden message on the top of the image. So let's see how this is run. So I have this image here, bharatmata.png. Let's see how we can hide any message in this case. So I will run python encode, then first of all is the -i image path, which is this one, then -m message. So message will be Vande Mataram, which is a Sanskrit word, and then like how we want to save it. So let's save it as encoded img.png. I run it, and yeah, so it says message is coded and saved in the images folder. So this is the images folder here, so it is saved inside this. Now if I want to decode it, I will need to run python decode.py and then the path of the coded image. So if I run this, I get the message as Vande Mataram. Now just to do it in a more cooler way, I will pass this function here, and now we will have the final message which will be printed on the image. So this looks cool. So yeah, that's it for the video. Bye.